Electric field intensity. If we now consider one charge fixed in position, say q sub 1, and move a second charge slowly around, we note that there exists everywhere a force on the second charge. In other words, this second charge is displaying the existence of a force field. Call this second charge a test charge q sub t. The force on it is given by the Coulomb's law. The Coulomb's law. F sub t equals q sub 1 times q sub t all over 4 times pi times the permittivity constant r1 sub t squared times a1 sub t. Writing this force as a force per unit charge gives F sub t over q sub t equals q sub 1 over 4 pi times the permittivity constant r1 sub t squared times a1 sub t. The quantity of the right side of this equation is a function only of q sub 1 and the directed line segment from q sub 1 to the position of the test charge. This describes a vector field and is called the electric field intensity. We define the electric field intensity as the vector force on a unit positive test charge. We would not measure it experimentally by finding the force on an IC test charge. However, for this would probably cause such a force on q sub 1 as to change the position of that change. Electric field intensity must be measured by the unit newtons per coulomb and the force per unit charge. Again, anticipating a new dimensional quantity, the volt, and having the label of joules per coulomb or newton meters per coulomb, we shall at once measure electric field intensity in the practical units of volts per meter. Using a capital letter for electric field intensity, we have finally E equals F sub t over Q sub t. This equation is the defining expression for electric field intensity, and the equation E equals Q sub 1 over 4 pi times the permittivity constant R1 sub t squared times A1 sub t is the expression for the electric field intensity due to a single point charge Q sub 1 in a vacuum. In the succeeding sections, we shall obtain and interpret expressions for the electric field intensity due to more complicated arrangement of charge. But now let us see what information we can obtain from the previous equation, the field of a single point charge. First, let us dispense with most of the subscripts in the equation, reserving the right to use them again anytime there is a possibility of misunderstanding. We should remember that r is the magnitude of the vector r, the directed line segment from the point at which the point charge q is located to the point at which E is desired, and A sub r is a unit vector in the r direction. Let us arbitrarily locate q sub 1 at the center of a spherical coordinate system. The unit vector A sub r then becomes the radial unit A sub r, and r is r, hence E equals Q sub 1 over 4 pi times the permittivity constant r squared times A sub r, or ER equals Q sub 1 over 4 pi times the permittivity constant r squared. The field has a single radial component and its inverse square law relationship is quite obvious. Writing these expressions in Cartesian coordinates for a charge q at the origin, we have r equals x times a sub x plus y times a sub y plus z times a sub z, and a sub r equals A sub r equals x times a sub x plus y times a sub y plus z times a sub z over the square root of x squared plus y squared plus z squared. Therefore, E equals Q over 4 pi times the permittivity constant times x squared plus y squared plus z squared times x over the square root of x squared plus y squared plus z squared a sub x plus y over the square root of x squared plus y squared plus z squared times a sub y plus z over the square root of x squared plus y squared plus z squared times a sub z. This expression no longer shows immediately the simple nature of the field, and its complexity is the price we pay for solving a problem having spherical symmetry in a coordinate system with which we may temporarily have more familiarity. Without using vector analysis, the information contained in the equations would have to express in three equations, one for each component, and in order to obtain the equation, we would have to break up the magnitude of the electric field intensity into the three components by finding the projection on each coordinate axis. Using vector notation, this is done automatically when we write the unit vector. If we consider a charge which is not at the origin of our coordinate system, the field no longer possesses spherical symmetry nor cylindrical symmetry unless the charge lies on the x-z axis. And we might as well use Cartesian coordinates. For a charge q located at the source point, r prime equals x prime times a sub x plus y prime times a sub y plus z prime times a sub z. As we find the field at a general field point, r equals x times a sub x plus y times a sub y plus z times a sub z by expressing r as r minus r prime, and then er equals q over 4 pi times the permittivity constant times the absolute value of r minus r prime squared times r minus r prime all over the absolute value of r minus r prime equals q times r minus r prime all over 4 pi times the permittivity constant times r minus r prime cubed. Earlier, we defined a vector field as a vector function of a position vector, and this is emphasized by letting E be symbolized of a position vector, and this emphasized since the Coulomb forces are linear, the electric field intensity due to 2-point charges Q1 plus R1 and Q sub 2 plus R sub 2 is the sum of the forces on Q sub 1 caused by Q sub t and Q sub 2 acting alone, or the equation ER equals Q sub 1 over 4 pi times the permittivity constant times the absolute value of R minus R sub 1 squared times A sub 1 plus Q sub 2 over 4 pi times the permittivity constant times R minus R sub 2 squared times A sub 2, where A sub 1 and A sub 2 are unit vectors in the direction of R minus R sub 1 and R minus R sub 2. The vectors are R sub 1, R sub 2, R minus R sub 1, R minus R sub 2, A1, and A2. If we add more charges at other positions, the field due to n-point charges is ER equals Q sub 1 over 4 pi times the permittivity constant times the absolute value of r minus r sub 1 squared times a sub 1 plus q sub 2 over 4 pi times the permittivity constant times the absolute value of r minus r sub 2 squared times a sub 2 plus q sub n over 4 pi times the permittivity constant times the absolute value of r minus r sub n squared times a sub n. This expression takes up less space when we use summation sign and a summing integer m which takes on all integral values between 1 and n. A sub r equals the summation of q sub m over 4 pi times the permittivity constant times the absolute value of r minus r sub n squared times a sub n. When expanded, it is identical with the previous equation, and students unfamiliar with summation signs should check the result. This is Kimberly and Kawili, ECE 3201.